So let's start a new one today. So review of lecture 17. We showed that K two-noded beam T1 theta 1 T2 theta 2 is given by EI by L cube 12 6L minus 12 plus 6L 4L square minus 6L 2L square 12 minus 6L 4L square, the symmetric part of it. This is what we have used, and using this, what we have done is this is a stiffness matrix, and then for the body forces, okay, for the, let's say, for when you are having some distributed loading, W is a function of X, then we said that we can use F body forces is nothing but integral W and transpose dx. This is one thing we have studied, and similarly we showed that for the uniformly distributed load, when W of X is equals to constant, then we got consistent load using consistent loading, that is, this is equal to, so I will come to that. The equivalence is not this one. So what we said was, we took a fixed beam, and if you have a constant thing, the reaction forces for this is given by and so what we said was, and this is the reaction forces. So the reaction forces of this condition, which is same as so since these two has same reaction forces, then we say that instead of this we would use this as a consistent loading. So when we have this one, we say that the consistent loading so F loading is taken as minus WL by 2 and W. This was the consistent loading for this case when W of X is a constant. Most of the time people use in this method. Then we used a case of let's say this is point load. For the point load we explained that when you have a point load at a distance A, then our loading would be such that it is P times N1, P times N2, P times N3, P times N4, or simply saying P N transpose at X is equals to A. And then we have concentrated movement, that is in the next case is it is located at A. Then we showed that for this the loading would be M into d by dx of N transpose evaluated at X is equals to A. So this is what we have developed in the previous class. And then after knowing how to handle the point movement, point load, distributed loads of different kinds, then we started going and looking into a simpler example. The example 1 which we have started solving yesterday was a simple beam with one end fixed, another end pin, and there was a load and a moment M and P which are both are equal to 1000 was acting at a distance L. This is L. So this was the beam, this was the boundary conditions. So this is a fixed end boundary condition, this is the thing. So what we are doing is we were trying to solve this using finite element method. I could have solved it using one single element, but however the choice that we have made for this simple example is we discretized this given beam into two elements such that this length is L, this length is L, this is node 1, node 2 and node 3. This is what you call it as mesh or discretization. So then so that is, this is our element 1 and this is element 2. We know that the K for the element 1 is given by EI by L cube. Let's say the bending stiffness for the entire beam or the flexural rigidity of the entire beam is EI. So in that case, we have shown that the stiffness matrix for the first element is given by 12, 6L minus 12, 6L, 4L square minus 6L, 2L square, 12 minus 6L, 2L square. With these things has the degrees of freedom such that, so anyway, let me separate the beams and write it. This was the first beam, which is node 1 and node 2. The second beam is beam element. Second beam element is, this is 2 and 3. And the degrees of freedoms on each one of them would be d1 theta 1, d2 theta 2. Again, this one is also d2 theta 2, d3 theta 3. That is nothing but this is d1, d2, d3, d4 and d5, d6. Okay, so that means we have these things as the stiffness is correct. This is again d1, d2, d3, d4. Similarly, we have, which is also same because the length of the both the elements has beam element happen to be same L and the stiffness is also EI. So it bears the same stiffness matrix. So it would also have very similar things. Six L minus 12, 6L, 4L square minus 6L, 2L square, 12 minus 6L and 2L square. These are with respect to degrees of freedom, which is corresponding to d3, d4, d5, d6, d3, d4, d5, d6. So then what we did was we did the assembly. The assembly K G was such that with respect to d1, d2, d3, d4, d5, d6, d7 and d8. Sorry, we have only up to d6. So such that our first stiffness matrix would come, let me write here also the guidelines: D1, D2, D3, D4, D5, D6. The first element stiffness was coming and sitting here from D1 to D4. This is also D1 to D4. While the second element stiffness was coming and sitting from here D3 to D6, D3, D6. So here you have addition of stiffness coming from the element 1 and the element 2. Here this is only stiffness coming from the element 2. Here the stiffness is only coming from element here 1, and here there is no stiffness coming out. So this is 0. So, and we showed that after assembly the final form looked something like this. Final form was 12 6L minus 12 minus 6L sorry, it is plus 6L and 4L square minus 6L this is 2L square this was 24 this was 0 this was 8L square this was minus 12 plus 6L this was minus 6L this 2L square and this one is 6L minus 12 minus 6L 2L square this was again 0 and this happened to be 12 minus 6L minus 12 6L 6L 2L square. This was the stiffness what we have got from the assembly of the previous thing. So the other elements are all zeros. When I wrote a big they're present in here. So this was 0, this was 0, this was 0, this was 0, this was 0. Now this 24 came from addition coming from 12 from one thing, 12 from another thing. This is minus 6L coming from green and red is plus 6L. Similarly, that's how it has become 0. 4L square coming from one thing and 4L square coming from the red one. So from element 1 and element 2. So together this was this thing. Now we have a global which is this is nothing but assembly of stiffness matrix. Now later we also showed that our Fg is equals to union of union of f of element 1 and f of element 2. Okay, for the element 1, what we said was we put the loads here and a moment which is 1000 each. Then accordingly 1 was happened to be 0, 0 minus 1000 vertical load acting on the downward side and a movement which is a sagging movement, so it is positive. Next, for the f for the element which is nothing but f1, f2, f3, f4 in the global things, f for the element 2 is nothing but all are zeros because there is no loading on the element 2, so that is nothing but for f3, f4, f5, f6. You should understand that this f3, f4 are the loading at the node 2 coming from the element 2, and this f3, f4 is the loading coming from the element 1. So these are a part of f3 in the global assembly. So where global f is nothing but f1, f2, f3, f4, f5, f6, that implies this is 0, 0, but f3 is coming from here and f3 is also coming from here. So this contribution is minus 1000, this contribution is 0, so together is minus 1000. This is 1000, this is 0, together contribution is 1000, this one 0, this one 0, coming from only these two things. And then what we said was our degrees of freedom, global degrees of freedom, is similarly would be d1, d2, d3, d4, d5, d6. Now it is true that when we assemble the things, the total kg is equals to d global into f global. However, to determine all the unknown things here, you cannot invert this. This is singular or non-invertible. The reason is we haven't imposed kinematic boundary conditions. So what are the kinematic boundary conditions for our problem? Kinematic boundary conditions for our problem are one end is fixed and other end is on the pin. So if one end is fixed, that means this is y is equals to 0 and dy by dx is equals to 0 at x is equals to 0 and y is equals to 0 at x is equals to 2l. Imagine this x is measured from the global things. If I measure this thing from this, then the new x dash or the new local coordinate system, this would be L, because this distance is L and this distance is. Here I wrote the boundary condition in terms of global coordinate system x. That's the reason to write it at. Now that means if I translate it in terms of the degrees of freedom, I know that at this there is node 1 and node 1 has a displacement, transverse displacement 0 and the rotation 0. That means d1 is equals to 0 and theta 1 is equals to 0. Similarly, at this place the displacement is nothing but d3, which is nothing, which we already call these things as capital D1, this is capital D2, and this is capital D phi. So our D global can be split into D unknowns and D knowns. So when I split it in this fashion, then what I get is our unknowns are, I don't know what is D3, D4 and D6, whereas I know D1, which is D1 is equals to 0, D2 is equals to 0, D5 is equals to 0. So D2 and D5. So these are things. So anyway, these all values are equals to 0. So anyway, this is a 0 vector. So now that can be split into K unknown unknown, K unknown known, K known unknown, K known. So how would you determine this? That means you want a contribution with respect to D3, D4 and D6 only, right? So to do that, I take this big matrix, which is my global matrix, and I strike whichever is known to me. The things that are known to me are D1 is known to me, D1 is known to me, so this is striked off. D2 is also known to me, so this is striked off, and D5 is also known to me, so this is striked off. Similarly, in the columns also I know, so I strike off this fellow, I strike off D2, I strike off D5. So when I strike off all these things, the remaining things is my KU. U. So KUU consists of the things which are not at all striked off. That is 24, 0, 6L, 0, 8L square, 2L square, 6L, 2L square and 2L square. So this is the thing that we are having it after kind of condensing it. So we condense this one to get only the KUU matrix. So similarly, KU is just take the things which are horizontally kind of striked off once. So horizontally only striked off once is the ones. So K means knowns. So the row, these are the rows and these are the unknowns. So rows are striked off, and if it is unknown, it is not striked off along the column. So that's the reason I pick these 12 minus 12, 6L, 0, minus 6L, minus 6L, 2L square 0 6L 2L square and 2L square. Now why I have only used this thing? Because my D known are all zeros vector. So that's the reason using the splitting of this equation. So if I just take this, I can split this and write it as, just a minute, file save. So this can be written as this can be written du and d knowns is equals to f u if a. So anyway, this is all zeros. So this into this, the first equation would alone survive it as kuu into du is equals to fu, right? And the second equation is nothing but, okay, let's take the first equation, let's finish it. So now du are the unknowns and this matrix is not singular. When does it becomes non-singular? When all the, so this is non-singular. When does it become non-singular? Is when the structure is constrained enough to arrest all the rigid body motions. As we have seen earlier, one side was the fixed end, which has constrained both the rotation as well as the vertical displacement. And in fact, this structure is overly constrained because the other end was a pin structure. Even without that, it would have been constrained enough. So this KUU would obviously is non-singular. So you can check it out. Maybe I'll show it in a couple of minutes. Next, this and hence invertible. So that means du is KUU inverse into FU. So let us see what is that. Du is nothing but D3, D4, D5, sorry, D6 is nothing but inverse of 24 EI by L cube, 24 0 6L 0 8L square 2L square 6L 2L square 4L square inverse into what is Fu? Fu is nothing but F3, F4 and F6. We know F3 is equals to minus 1000, this is equals to plus 1000, and this is equals to 0. Right? So let us try to solve these things. So for that, I'll quickly show you MATLAB. So let's switch to MATLAB. So at this point, if you have any questions, I will stop here before I move to the MATLAB session. Okay, the sixth row, sixth column was written as 2. Let me just check it. Thanks about it. This one is from this guy as A in the MATLAB. So KUU is equals to A star 24 0 6L and 0 8L square and 2L square and 6L to KUU. Now I need inverse of KUU, which I store it as IKUU is equals to inverse of KUU. So if I type that, this is my K inverse, which is something looking in this manner, which I will use it and put it back here. So it happened to be the inverse of it is equals to 1 over A, that is L cube by EI times 7 by 96 1 by 32L minus 1 by 8L 1 by 32L 5 by 32L square minus 1 by 8L square minus 1 by 8L square minus 1 by 8L square plus 2L square times minus 1000 plus 1000 and 0. So then you can quickly write it down, this one as L cube by EI into 1000 The first one is with a minus 7 by 96 plus 1 by 32L. Anyway, this is 0. The next one is minus 1 by 32L plus 5 by 32L square. Third one is plus 1 by 8L square minus 1 by 8L square is the solution. So I hope this is not L square, so I made a typographic. This is not L square, this is L. So let me just compare it. 7 by 96, 1 by 32L minus 1 by 8L, 1 by 32L, 5 by 32L square minus 8 by L square minus 8L minus 8L square, 1 by 2L square. So this is, if you just put your corresponding L, EI and the other values, that only EIL, you can simplify it further. So with this we have solved our du, so which is nothing but these are the values for the first one is D3, D4 and D6. Okay, so these are our values corresponding to that. Further, to find the reaction forces, then we make use of this equation, which is this equation, the second one, and based on the second equation, Ku times du is equals to Fk. These are nothing but your reaction forces. These reaction forces, since you obtain du here, since you obtained your du just above, du is obtained by this, and your kku is given by this, you can determine wholly just by multiplication what are your reaction forces. With this we'll complete the first problem. At this point of time I will take a break and I will ask you if you have any questions regarding to the problem 1. EI. Now the mesh or the discretization for this problem would be defined as this manner. So this is node 1, node 2 and node 3. Node 1, node 2 and node 3, element 1 and element 2, and P is acting at here, roller support is here, and the fixed end is here. So this is however discretization. So let me take it again. So that is, this is element 1 with this node 1 and node 2, and element 2 which is node 2, node 3. Okay, this is element 2. If you look at it, each one is of length L. So even in the problem 1 we have 2 elements, so entire procedure is same. So the purpose of choosing this problem is I don't want to repeat all these things twice today. So the K for the element 1 and K for the element 2 remains as it is because it is of the same thing. So I'll take this again and use it elsewhere. So K for the element 1, this is for the element 2. So the same things remains true. So because our degrees of freedom are again d1 theta 1, d2 theta 2, d2 theta 2, d3 theta 3. That is nothing but our degrees of freedoms are capital D1, capital D2, capital D3, capital D4, capital D5, capital D6. So the stiffness matrix for this both the things remains the same. So and the global assembly is also same. So I will use the global stiffness which is given by this thing will also remain same. So the so K global, which is assembly of these two in the similar manner, is also remains the same. So anyway, since I made the mistake, I have to rectify it. This one is not 2L, as somebody has mentioned earlier. This is the only thing is 4L, which was a typographic error. So let me also correct it there. Anyway, so let's come back. So this everything remains same as it is. Now let's see our forces. Let's compute the forces on the element 1. Forces on the element 1 is we have this element 1 which is like, and a load is acting at this place P and nothing else is there. So that means the F is nothing but minus P 0 0 0. Now what is the load on the element 2? The element 2 was something like this. There were no loads on the element 2, so all are zeros. But we know that this is F1, F2, F3, F4. These are F3, F4, F5, F6. This is node 2, node 3. So let me see if I have any questions from the gallery. No. Okay. So in fact, we should not put these things as zeros. If you put the boundary conditions, you could clearly see that you can write it as your reaction forces, but I will tell you later how to do that. Or you can as well as put the reaction forces. So actually 2 comes with, this point comes with a reaction force, which is, let's say, V, and some moment which is m at this place. So you can ask, so let me, so let's not write it, let's only write the point loads at this point. And so this is only coming from the point loads. The reaction forces will come to it at a later point. So so this is only there when the things are not constrained. Now if you try to constrain certain things, those places your reaction forces will come. So we'll replace it with the reaction forces at a later point. So anyway, we cannot solve these things because this is non-singular. So for that, what we need to do is we need to condense it. We need to apply kinematic boundary conditions. So when you apply kinematic boundary conditions, we know that for the given problem, which is for this problem, the degrees of freedom are d1, d2, d3, d4, d5, d6. This is nothing but the d3 and theta 3. We know that the displacement at this place is 0 and the slope is also 0. Further, here d3 is kind of is a vertical displacement. Because it is on the roller, it has to be equals to 0. So d3 is equals to small d2 equals to 0. And these things are known to us. So since these are known to us, so what we will say is our D knowns are D3, D5, D6. Our D unknowns are D1, D2 and D4, which is nothing but D1, theta 1 and theta 2. Okay, that's having said that one. So now the reaction forces would be F. K would be, let's call it as the reaction force V2. So there would be a reaction force V3 here and a moment M3. So this would be V3 and minus, since it's a hogging moment, it is minus M3. These are the reaction forces. Fu is nothing but directly what we get it from this, which is D1. If we remove the, these are at the places of D3, D5, these are with respect to F3, F5, F6. So if you remain it, we will have F1, F2 and minus P 0, 0 in this case. So now when you take these things, we have to solve it. To solve it, let us do again the same exercise. I will take this thing and try to condense it. So now my unknowns are 3, 5, 6. Sorry, unknowns are 1, 2, 4. So my knowns are 3, 5, 6. So I will strike off the knowns 3, 5, 6. So I take and I will strike off the third thing and fifth one and the sixth column. Similarly, the third row, fifth row, and the sixth row has been striked off. If you have striked off in this manner, then our K UU in this case, which is different from the previous one, is the one which doesn't have any horizontal or vertical line. So that is 12, 6L, 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 4L square, 2L square, 6L, 2L square, and 8L square. That which I'm going to write it here. So this is 12, 6L with an EI by L cube. I think I forgot it here also. With this EI by L cube is there. 6L, 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 4L square, 2L square, and this is 6L, 2L square, 8L square, and similarly KU. That means the rows, this is like the rows which are striken, and columns which are unstriken. So rows which are striken are these things, and the columns which are unstriken are these three. So the K is EI by L cube minus 12 minus 6L 0 0 0 minus 6L 0 0 2. Now since you know KUU, DUU, again since our D known are all zeros, so we can write KUU into DU is equals to FU, or DU is equals to KUU inverse of FU. So that is our D1, D2, D4 is the inverse of 12, 6L, 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 4L square, 2L square. Six L, six L, 2L square, 8L square, EI by L cube whole inverse into minus P 0, 0. Now let us try to find again the inverse of such kind of things. Again I will call this fellow as this, I will call it as A. Then using the MATLAB. KUU, again let's clear everything. Since A and L are our symbolic variables, and KUU is equals to A star 12 6 L 6 L and 6 L 4 L square 2 L square 6 L 2 L square 8 L square. Let us see for 12 6L 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 4L square 2L square 6L 2L square 8L square. So KUU is this one. Okay, with EI multiplied to it. Now I want inverse of KUU is equals to now let me write the inverse. So D1 D2 D4 is equals to L cube by EI into 7 by 12 minus 3 by 4L minus 1 by 4L minus 3 by 4L 5 by 4L square 1 by 4L square minus 1 by 4L 1 by 4L square 1 by 4L square. Let me just compare my result. My 7 by 12 minus 3 by 4L minus 4 by L 4L 5 by 4L square 1 by 4L square. Great. So times minus P 0 0. That says that this is nothing but D1 D2 D1 theta 1 and theta 2 is nothing but D1 is equals to, if you just multiply it, this is only the first column is there that would sustain with a minus sign multiplied with the P, so I can easily write D1 theta 1 theta 2 as P L cube by 3 EI with a minus sign. Just retain the first column minus 3 by 4L and minus 1 by 4L. So that means my displacement is equals to minus 7 PL cube by 3I. My slope at that place is just a minute, I just made a mistake. This is PL cube by EI. So I don't know why I have written that statement. So 7 PL cube by 12 EI is plus 3 PL square by 4 EI L square by 4 EI. So that's how we solve the problem. Once you know this du using the second equation, which is you'll be getting the reaction forces at the end. So just use the above this KUU and multiply this vector du, you'll get the reaction forces, which would be the vertical reaction force at the second node and the vertical reaction force at the third node, and the rotation the movement at the third node. So which I will just leave it for an exercise because it's a simple multiplication. So at this point of time I will stop again and see if the gallery has some questions, because the first two problems has so many things are in common except the boundary condition and the loading. So is something like this. With point load, since we got a negative displacement, that means the D1 is in this direction. This would be our elastic profile. So if you look at the things, so what we have determined is this is the D1 and this the theta 1, and this is the theta 2, sorry, the theta 2 that we have determined based on the values. You can clearly write what's the the things. So this D1 is coming out to be minus 7 PL cube by 3EI, and this theta 1, which is in the positive slope, is 3 PL square by 4EI, and this one was PL square by 4EI. This would be the deflection profile obtained from the things. So with this we will complete the problem, example problem, and then we will go for the next one. So let us solve some simpler problem again. So with a little bit complicated things. So let us consider the third problem. Let me see if I have any questions. Okay, there a uniformly distributed load on a cantilever. Let us take the load to be 20 kilonewton per meter, and let's take length is equals to 100 meters, and the stiffness as EI. So now let us try to solve this problem in several ways. The first one is one element solution. In the one element solution, the entire length of the beam is the same, which is nothing but is the node 1, node 2. The length is 100. So the degrees of freedom would be d1 theta 1, d2 theta 2, and that is nothing but your degrees of freedoms are capital D1, capital D2, capital D3, capital D4. Okay, so anyway, we know the K for the element stiffness matrix for a single element is equals to EI by L cube 12 6L minus 12 plus 6L 4L square minus 6L 2L square minus 12 plus 6L minus 6L 2L square. This is 12 and this is minus 6L minus 6L and this is 4L square. So there is nothing big deal about it. So this which we have obtained, we'll have it as it is. Okay, so let us take our E is equals to um, so let's have such some values. Okay, so then we can compute our this thing using Let us take this one as mm instead of uh, so that we can have the meter would be very huge. So let us make it into 100 mm and 20 kilonewton per mm. So in that case, we have to just have to watch for our units. So this is EI is in Newton per mm4 mm square, and I is mm to the power of 4. So this one is 12, and this one is 6 into minus 600, 2 into 10 power 4 minus 12 minus 600 plus 12 plus minus 600 plus 600, 2 into 10 power 4 to minus 600 and 4 into 10 power 4, and our EI can also be replaced as into 100 divided by, so this boils out to be anyway. So let me just make the simplification here itself. So this value comes out to be, so now let us try to get this is our stiffness matrix. So this is our, there is no assembly in this because our element stiffness matrix itself is our global stiffness matrix, and then we know that the degrees of freedom are with respect to d1, d2, d3, d4, d1, d2, d3, d4. So anyway, before I so now let us this is non-singular matrix. We have to apply the kinematic boundary conditions. To apply the kinematic boundary conditions, we need to know how the beam looks like. So the beam here is fixed at this place. That means our d1, this is equals to 0, and theta 2, theta 1 is equals to 0. And d1 theta 1 both are equals to 0, and hence that means capital D1 and capital D2 are equals to 0. So that means our D knowns are D1, D2, and D unknowns are D3, D4. Now what we'll do is we will try to obtain our KUU. KUU is obtained by knocking off the knowns, which are nothing but D1, D2, D1, D2. So that means our KUU is just given by 3 into 10 power 3 into 12 minus 600 minus 4 into 10 power 4 is our KUU. So now our FU, we need to obtain our F. So F for the element 1 is nothing but we have to make use of our consistent loading. So the consistent loading would be minus WL by 2 WL square by 12 so this would be minus 20 into this is 20, this is kilonewton, so we need to mind our units. So this is our loading. So what we'll do is, since the we are coming to the end of the class, I will try to continue this math, and because this problem has to be solved with respect to one element, and then we have to also solve the same solution using analytical method, which is very pretty simple, which we might have already done in some strength of materials course, and then we'll compare it with respect to 2 element 3 and some other higher elements, and we'll show that how does a finite element solution would converge with respect to H convergence. H convergence is nothing but with the decrease in the mesh size will increase the number of elements, and how does our exact solution and the approximation obtained from both the things will uh, fall under each other. To compare those things, we need to work out some math. So since we only have a couple of minutes left, this is a right choice for me to stop at this given point of time and continue tomorrow again at 2 o'clock. Okay, so see you guys tomorrow at 2. If you have any questions at this point, I will take those things. Moment, and my degrees of freedom are d1 theta 1 d2 theta 2. You see the sign convention in which I am measuring my degree of freedom. So its force conjugate should also be, the forces should also be in the same direction. So this is the force at this place, moment at this place, something like that. Now because of the consistent loading which I have invoked, my forces were WL by 2 in the this direction, WL by 2 in the downward direction, WL by 2 here in the anti-clockwise, and WL by 2 by 12 clockwise at this here. WL by 2 is in the opposite directions to each other. That's the reason I put WL minus WL by 2 minus WL by 2. Whereas the moments here is a positive bending moment. So I just consider in that manner. So with this, what I will do, I will try to repeat this in the next class again, and we will pursue it further down tomorrow. Okay, so I will try to explain it tomorrow once again before starting into going into the problem further. So we'll continue tomorrow, and we'll resume at the same place where we have stopped today.